the next topic, which is transformers. Okay? So the topic that we are going to cover under transformer basically are, let me talk about today first. I will be talking about types based on both application as well as construction and single phase and three phase. These are the various types we will be talking about. So in the process, we will also be talking about applications. Right? So we will be talking about the applications as well. Then we would be talking about EMF equation for a transformer. After talking about the EMF equation, it will become clearer why we have V1 by V2 equal to N1 by N2. So we will talk about voltage and current relationships. So the next thing that we will be talking about is voltage and current relationships. After this, we will talk about ideal and non-ideal transformer and then the phasor diagram. This is the sequence. After that, we will worry about what further we will discuss. Okay? So I will then cover ideal and non-ideal transformer, which will take us to equivalent circuit and so on and so forth. Okay? Fine. So the major application of a transformer is to step up and step down the voltages, and this will be used in transmission as well as distribution. So normally the generated voltage level, if we look at, is generally about 11 to 30 kilovolts. In fact, I should say 15 to 30 kilovolts. The limitation is because of the insulation that I have to put around the windings, which are placed inside the slot. So when I have slots within the machine and I put conductors inside, if the conductor is having extremely large voltage, I have to insulate it against the slots as well. So the insulation will become thicker and thicker if I go for higher and higher voltages. So that essentially prevents me from having extremely large voltages, because the insulation will become prohibitively thick. I will not be able to place it properly inside the slots. And that's the reason why we generally limit it to less than 30 kilovolts at any rate. But if I try to transmit the power at 30 kilovolts, the current will become enormously high, unhandleable, literally, because of which I necessarily need to step up the voltage so that I would be able to keep the current within limits despite, transmitting extremely large amount of power, right? So when we talk about transmission capacity, the overall generation capacity of our power grid right now is about 210 gigawatt. Okay? This is not including all the renewables that are being added every day. So 210 gigawatt of power is being transmitted all over the country all the time. So if you think of transmitting this at lower voltage level, it is going to be unimaginably large current. That's the reason why we step up generally the voltages. So first application I would say is stepping up for transmission. And very clearly on the other side, I have to step down for distribution. Mostly these two are done in three phase, not in single phase. Only the distribution at domestic level is done as a single phase configuration, right? And most of the power transmitted for any industrial use is all in three phase. Only exception is our suburban train system. Normally, if you look at Bombay or if you look at Chennai for that matter, very old suburban train system, what is there, which takes people from one station or one locality within the city to another locality, most of it is in single phase. It's not in three phase, although the power capacity is pretty much high. It is generally 25 kV. What is being transmitted there is 25 kV, at 25 kV level. Then it is stepped down within the railway car, which is known as the electric engine. And there is a rectifier sitting, which would be converting that into DC, and then the DC motors, DC series motors drive the electric vehicle. That's what is done in Bombay, the old system. No, newly there have been some conversions to AC. For example, if you look at the Western Railway route in Bombay, that is, most of it is now converted into AC. Whereas, if you look at the Central Railway route in Bombay, that is mostly in DC. Okay? So, that is AC transmitted, converted into DC, and the DC motor is driving the vehicle. That's what I mean by DC. Basically, the drive train is DC drive train, basically. Right? This particular railway electrification is done with the help of single phase AC, because the return route is not there at all. Return conductor is not there at all. The rail serves as the return conductor. There will be generally a line which is the overhead transmission line, somewhat like this. And you would see that a U-shaped conductor will be touching from the train. So this is actually your train, let us say. Okay? These are the wheels. I am just arbitrarily drawing a diagram, basically to represent. So this particular thing is generally known as the pantograph. This is the pantograph. So pantograph basically is a kind of a brush kind of arrangement, which is actually made up of a thick conducting material which is insulated by, whatever is the insulator. They may have some plastic, bakelite and so on, and then that is having a U-shaped conductor which is sliding over the overhead transmission line to collect electricity. So this is the only conductor that is being used throughout the railway electrification zone. So this is the conductor or overhead conductor that we use. And whatever is the rail here, that is supposed to be our return conductor. So basically, it is going to save on huge amount of copper. That's the reason why single phase transmission is being used only for traction application. Of course, inside the electric car, there will be a transformer and there will be a rectifier normally. Both will be sitting there along with a DC motor drive. That is how the entire thing is driven. So I would say that this transformer, which is stepping up for transmission, we normally call that as power transformer. Whereas what we use for distribution, we will call that as distribution transformer. So power transformers normally step up the voltage from the generator, and distribution transformers normally step down the voltage from the transmission line and send it to whatever is your domestic application or industry applications and so on and so forth. Again, in terms of functionality, the power transformers will be functioning only when the corresponding generator is generating. Let us say the generator has been shut down for some reason, maybe for maintenance, maybe there is a fault, maybe some prime mover has gone crazy, something is wrong. So you are shutting down the generator. If you are shutting down the generator, then the transformer will not be energized. So the power transformers will be functioning only when the corresponding generator is functioning, and it will be almost functioning at 100% load to its fullest capacity. If I say it is a 200 MVA generator, it will always be delivering a power corresponding to 200 MVA normally. So power transformers will be functioning along with the generator to its fullest capacity normally. Whereas distribution transformer will be functioning no matter what 24/7, all the time, 365 days in a year. Because let's say I have a distribution transformer probably which is supplying power to LHC. Even if one class is happening, I have to energize the transformer. Even if no classes are happening, probably in the anticipation that something might happen at any time, I have to have it functional most of the times. Similarly, any domestic environment, if I look at a locality, I can't say all the loads will be on all the time. Even if one customer is, wanting the power, I can't switch off anything. So distribution transformers normally will be energized 24 hours a day, 365 days in a year. All the time they will be energized. So there is no guarantee that distribution transformers will function at 100% load. It may be much less than what is actually it is rated for. Is this understood? Fine. So you are basically going to look at this difference in terms of later on the design, efficiency calculations and things like that. Right? We'll be looking at it later. So these are two specific applications that I talked about for transformer. Apart from that, I may have a transformer for impedance matching. You guys must have studied about something called maximum power transfer. If I say that the source impedance is RS plus JXS, this is the source impedance. The load impedance, if it is actually RL plus JXL, if I may say, when I have RS equal to RL and XS equal to minus XL, I am going to have maximum power transfer. Right? So whenever I have an intervening transformer between a source and a load, I will be able to make or create a situation as though the load impedance and source impedances are being matched depending upon the turns ratio. You guys know that from the secondary side, whatever is the impedance, I can look at it from the primary side as N1 by N2 the whole square multiplied by whatever is the impedance on the secondary side. So by having an appropriate turns ratio, I can create a situation such that the load impedance and the source impedances are matched. This is done very often in many of the electronic circuits, so that the maximum amount of power transfer takes place to the load from the source, because the available power itself will be pretty small and I want to transfer as much as possible to the load. So I would like to match the impedance. This is one of the applications of transformer. Another application I would say is isolation. Isolation is between a high voltage and the low voltage, I might like to have some amount of, separation between their grounds. I don't want them to be connected to the same ground. So earthing or grounding, what you do for a high voltage source will be separated from the low voltage side with the help of transformer, because the transformer does not have any direct electrical connection. It is coupled only by electromagnetic induction. It is only magnetic coupling. So there will not be any direct current flow from the high voltage side to the low voltage side, or low voltage side to the high voltage side. So they are not conductively connected. They are not connected through a conductor. So if there is something going wrong on one side, it will not or it may not affect the other side. So I would like to isolate a high voltage side from a low voltage side, or a high power side from a low power side. For example, if I am controlling the speed of a DC motor, which you all did in ELL 100 course, right? what I am supplying as power to the DC motor may be at kilowatt level. But if I am using a transistor or something to control the power to the DC motor, the transistor will be turned on and off with a base drive. So that base drive will be at 15 volts level or even less. Whereas the motor will be operated probably at even 1 kilovolt level. It is possible. So I might like to have the isolation between the motor and the transistor base drive circuit. That can be done very nicely by using a transformer. So generally transformers are used for isolation when I require some protection. So this will actually give me some protection against fault in the high power side. So in the high power side, if there is some fault, that will not affect the low power side. Right? I may have a computer microprocessor controlling my DC motor. I don't want the computer to conk out completely if there is a problem in the high power side. So I may use a isolation. Another application is for measurement. I mentioned about this already once. So this can be potential transformer. I may like to measure a 400 kilovolt quantity from a transmission level. I will not have a voltmeter of 400 kilovolt range. So I might like to step it down using a potential transformer and then give it to a voltmeter of a lower range. So essentially this is for measuring high voltages. Right? Similarly, I may have current transformer which will actually bring down the current value so that it is falling within the ammeter range. So this is essentially used for measuring high currents. But obviously this can be done only for AC measurement. It cannot be done for DC measurement. Obviously, it is only for AC measurement. Last but not the least, there are also auto transformers and tap changing transformer. AUTO, auto transformer, and also tap changing transformers. Auto transformer is, for example, a single winding transformer. So I may just have a winding which is wound on a core. I am not showing the core right now. I may supply the voltage until maybe, if there are 1000 turns, I may actually supply the voltage only until 980 turns. So what I am connecting is only to lesser number of turns than what is the total number of turns that are available in my transformer. Maybe I am connecting 230 volts here. So what I get at the output can go easily up to 250 volts. So it is like stepping up, not with two windings, but because the number of turns on the other side is slightly higher. So I am supplying the voltage only to, let us say, 900 turns, but what I am tapping at the output is corresponding to 1000 turns. So obviously if I am applying 900 volts to the 900 turns, then I will be able to get 1000 volts out of 1000 turns, which are the total number of turns in the transformer. There is no isolation here, clearly. The primary and secondary are essentially the same winding. Only thing is, less number of turns are there in the primary side and more number of turns are there in the secondary side. That's all is the difference, right? So this essentially will allow me to step up or step down depending upon how many turns I am tapping. So I am calling it as, I have got multiple number of taps. I may tap it from here, I may tap it from here, I may tap it from here. So I can call this as maybe tap 1, this is tap 2, this is tap 3. So I can have multiple number of taps and I can choose to tap any amount of voltage out of this auto transformer. I should be able to do this as per my requirement. Okay? So this kind of transformer is also known as tap changing transformer because you may change from one tap to another. These applications are very much prevalent in our substations and it may be there even in your generating station, switchyard. Because let us say my generator is generating 15 kilovolts and I am trying to step it up to 400 kilovolts for transmission. When I am having 400 kilovolts at the output on a nominal load, say 100% load, obviously there will be some internal drop within the transformer, within the generator because all of them are having some R and some JX. So depending upon the current that these equipment are carrying, I am going to have some drop. So I would say the voltage at the terminal of the generator will be 400 kV minus whatever is my R plus JX of the transformer and generator multiplied by the current. Of course, I have to include the power factor angle, no doubt. This is how I am going to get terminal voltage. If I switch off some of the loads are gone, then the current is going to decrease. If the current decreases, R plus JX multiplied by the new current will be definitely smaller compared to what I got earlier. So if the drop is lower, originally let us say I was getting 400 minus this drop was maybe 380 kV and I was expecting 380 kV only at the end of the generator terminal or the final terminal of the transmission line. But now it might go as high as 390 or even like 395 kV. My equipment may not be able to withstand the 395 kV. So I might like to put the tap at a lower number of turn. Are you getting my point? So if I put, originally maybe my tap was here, now I might like to put my tap at a lower point. If I put it at a lower point, even the incoming voltage is decreased somewhat. If the voltage is decreased, correspondingly I am going to have in the terminal also a little less voltage than what I was getting. So the tap changing transformer allows you to make minor adjustments in the voltage so that any higher drop or lower drop is compensated for. So that is the major advantage of tap changing transformer. So much so for the applications of transformer, this also gives rise to variations in the functionality of the transformer as power transformer, distribution transformer, measurement transformer, isolation transformer and auto transformer. So these are the various classifications of transformer as per the application. So let us try to look at another variation or classification in the transformer, which is actually single phase and three phase. Single phase transformer is commonly used only in domestic applications. Hardly ever you would see the single phase transformer in transmission or distribution application. Whereas three phase is always used in all transmission and distribution applications. Right? We also have one more type of classification based on construction. So based on construction, we may have something called core type construction or shell type construction. What we mean by core type construction is, let us say I am going to have probably a lamination somewhat like this. Right? Generally, laminations are made in such a way that they will be made by two pieces. One will be of C shape, if you may call this as C shape. Right? The other one is just a straight line or a rod kind of construction. Right? Now what I am going to do is to put one winding here, maybe another winding here. Right? So I call this as core type construction. Please note that only on one side of the winding I am going to have iron, whereas this side of the winding I am having air. Right? So naturally, if I look at any flux lines that are probably going to flow here, right, I may have something called leakage. These will be leakage lines. On this side, if I look at the leakage lines, I have a very, very small air path, not much of window available. But on the other side, huge amount of air is available. So in core construction, at least on one side, the windings are surrounded by air. Whereas on the other side, very closely, you are having the second limb coming up. Whereas in shell construction, I may have actually an E type of core. For example, I'm just showing that this is in the shape of E. This is how it is. And I'm going to have basically this as my core, and I'm going to close this with the help of, again, a straight line like this. Fine? So I may have basically, the winding rather put up only here in the central portion. So I may have primary and secondary both put up only in the middle portion of the winding, which means on either side I'm going to have iron surrounding it. So the reluctance in this case will be really, really low, because of which the entire magnetic field lines will try to confine themselves only within the core, either like this or like this. Hardly anything will escape into air. Whereas in the other case, because I have some larger amount of air surrounding the winding, I may have more number of lines leaking into the air. Some of them will definitely leak into the air in either case, but the number of lines leaking into air in this case may be slightly higher. So I will have basically these two types of construction. Here the leakage will be slightly more. And I should say very clearly, this is more expensive because more amount of iron will be needed to construct this core, right? So I will be needing more amount of iron to construct this core. So these are two types of construction. Depending upon where I can't tolerate more reluctance, I have to adopt this construction, shell type construction, right? One more thing we would like to do is, the core is constructed like this, I told you. Rather than basically having this C shape and a straight line kind of thing, just stacked one behind the other, we may like to have the second. If I say that this is the first stack, this is the first stamping, I would have the second stamping just the opposite of this. So I may have the C shape at the bottom, and I would have basically this straight line at the top. Are you getting my point? So I will put one behind the other so that the air gap does not become continuous. Are you getting my point? I will have a small air gap, whether I like it or not. I am going to have a small air gap here. In this case, similarly, I will have a small air gap here. I don't want this air gap to continue one behind the other continuously, because that will increase the reluctance. So I would like to put the first stamping with the straight portion at the bottom. I would like to put the second stamping with the straight portion at the top and vice versa. Continuously I'll do that, first, second, third, fourth and so on. The same thing I should be able to do here also. In one case on the top I can put the E, at the bottom I can put the straight line, and the second stamping will have the straight line at the top and E at the bottom. So I can do this alternately so that the air gap does not continue through the stampings. Are you getting my point? So the reluctance will be somewhat limited because I'm alternately arranging this. So these are some of the constructional details of the transformer. Normally the core material will be silicon steel and the stamping thickness will be anywhere between 0.3 to 0.5 mm. Each of the stampings will be having, this as the thickness. Fine? The question was, why don't we make the core as one single stamping which is in square shape or in E-closed shape? Invariably the windings are, really heavy. If the windings are heavy, it will be very difficult to actually make the winding manually or even machine wound windings around pre-processed core. Rather what you do is, you make the stamping in the shape of C. Then you just put the winding like you put a ring, right, in a finger. So you put the ring, and then close the other side. That is how generally the transformers are made, because the windings are extremely heavy. That's the reason. Got it? So you are essentially going to have a big problem. In fact, three-phase transformers are very, very difficult to transport. So whenever a power station is made, they rebuild the roads, rebuild the bridges, rebuild all the railway tracks to transport the transformer from, for example, BHEL Bhopal, BHEL Haridwar. Haridwar makes lots of transformers. So when Ramagundam plant was constructed in Andhra Pradesh, all those in between bridges, railway tracks and the roads were reinforced very strongly to make sure that it does not sink in completely. Otherwise you would have seen that the road or the tracks would have collapsed completely. So it's very important that the mechanical strength is also taken care of. Otherwise you would not be able to transport normally the three-phase transformer. That's one reason why three-phase transformers are normally made up of 3 single-phase banks. We never make the three-phase transformer directly as three-phase transformer. We try to make 3 single-phase transformers, connect them in star or delta externally, so that when you transport, it becomes simpler. And also, if you want to store some of the backups, you can always store a backup as a single phase rather than storing the entire 3-phase. So it saves on money, right? So that's the reason why normally 3-phase transformer banks are never directly 3-phase construction. It is 3 single-phase transformers connected in star or delta configuration. So let us now go to the analysis of a transformer. Let me just represent, schematically a single-phase transformer. So I would simply show that as 2 windings like this, right? And they will be essentially shown with the help of 2 parallel lines. The core will be shown with the help of 2 parallel lines sitting in between. Right? This is the representation of a transformer. So I'm going to apply maybe a voltage of V1 here, and I'm going to get a voltage of V2 as the output. Right? And because it is made up of silicon steel or a ferromagnetic material, to establish a flux which will cause electromagnetic induction in the secondary side, I would not require a large amount of MMF. The reluctance is really, really small, because the reluctance is small, to establish a nominal flux, I will require a very, very small amount of MMF. Ideally, I should say literally 0 MMF should do it. It's not true. Reluctance is not 0. Reluctance is some minimum quantity. So that reluctance multiplied by whatever is the flux that I want to establish, that is what is contributing towards the MMF. That MMF is a small quantity in a ferromagnetic core transformer. So I am going to say that to establish a flux in the core, right, minimum current is needed. Very minimum current is needed. This is because of the fact that I am having very, very low reluctance for the core material. Is that clear? Now, let us say I have the transformer and I have established a flux of phi, which is actually given by some phi m sine omega t. This is the flux that is established in the core. Assuming that I'm going to have a good amount of, permeability for the core, whatever is the flux that is linking the primary winding, the entire flux should also link the secondary winding. So this flux is not only linking the primary winding, so this is the flux linking the primary as well as secondary. Both are linked by the same amount of flux, right? So I can say by Faraday's law, the induced EMF in the primary or secondary will be d phi by dt. So I can write this as phi m omega cos omega t. This is what is going to be the induced EMF. So if this is the induced EMF, right, I can write this as phi m multiplied by 2 pi f multiplied by cos omega t, where frequency, f is the frequency at which the entire current or the flux is oscillating, at what frequency it is oscillating. Now, I can say that RMS value of induced EMF will be equal to 2 pi f multiplied by phi m divided by root 2, because it is cosinusoidal, right? The peak value of voltage is 2 pi f into phi m. I am dividing that by root 2 to get the RMS value. So this will give you essentially, if you calculate it, it will give you 4.44 f multiplied by phi m. This is what is going to be the voltage induced in a transformer per single turn. If I talk about one turn, the induced EMF is d phi by dt. If I talk about n turns which are connected in series, the total voltage induced will be n times d phi by dt. So I can say voltage induced in the primary, right, will be equal to, if I say this is ET, that is voltage induced per turn, I can just say this is ET multiplied by N1, where N1 is the number of turns in the primary. So I should be able to say ET multiplied by N2 will be the amount of voltage induced in the secondary. So from which I should be able to say V1 by V2 is equal to N1 by N2, which is the basic voltage equation of a transformer. Right? Is it fine? So let us try to now look at what happens when a transformer is connected to a load. Let me first represent a transformer on no load condition here first. This is my core, and I am showing as though primary is wound here and secondary is wound here, right? And I'm applying a voltage of V1 here. I'm expecting that a voltage of V2 I should get here. Currently, the secondary side is left open. And what is drawn by the primary here is only the current that is required to establish the flux. Nothing more than that. If I want to establish a flux, which is a nominal flux, I might require a very, very small amount of current because of the fact that the core is having high permeability, right? So, the current drawn by the transformer when the secondary is open circuited, that current is known as the no load current. When there is no load connected in the transformer, I may call this current I0 as the no load current. So, I0 is the no load current. This is the no load current of a transformer, right? And that will be really, really small because of the high permeability case of your core, ferromagnetic core. Very clearly, if it is an air core transformer, even the no load current will be very large. I hope you understand. Even when I don't have any load to establish the flux itself, I will require quite a good amount of current or quite a good amount of MMF. So, because of high reluctance of the air gap, right? So, if the core is made up of air, it is an air core transformer, then I am going to require a very, very large current even under no load condition. Got it? Now, let's say I am going to connect the load. So, this is my primary, right? And I have applied V1, and what I was having is I0. This was under no load, right? Now, I am going to connect the secondary to a load. So, this is the load, right? And let's say this is actually drawing a current of I2. When it is drawing a current of I2, right? Essentially, this current is also not going to keep quiet. It will definitely establish a flux. And when it is establishing a flux, it is again alternating in nature. Because V2 was alternating, I2 has to be alternating, and I will have definitely an alternating flux established. If this flux becomes additive to the original flux, the flux would eventually reach infinity. Very, very large value. So, obviously, it will be opposing the original flux. By Lenz's law, the new flux that has been established by I2 will oppose the original flux. And this I2 may be very, very large because it depends upon what the load is demanding. If I am having a 400 volts transformer and if I have only 4 ohm connected, then 100 amperes will be flowing. So, obviously, I am going to have a large value of current flowing as the load current. So, this large current flowing through the winding will establish a flux which will be actually opposing the original flux. If it opposes the original flux will be collapsing completely. It will be killed. If the original flux is killed, the transformer action ceases to exist. There is no question of any transformer action because only because of the transformer action I had V2, only because of V2 I had I2, and I2 has now come up to generate one more flux which has killed the original flux. So, entire thing has come to a standstill. So, what will happen is, if the transformer action collapses, if I have got V1 and originally I had got an induced EMF of E1, V1 was approximately equal to E1, assuming that the resistance is hardly anything within the transformer winding. So, now if flux collapses, I am going to have E1 becoming almost 0. So, if E1 becomes almost 0, the current that will be gushing into the primary winding, which will be V1 minus E1 divided by whatever is the impedance of the primary winding. That will become really, really large. Obviously, if E1 is diminishing, I will have the voltage difference between V1 and E1 actually drawing a huge current, which will be equal to V1 minus E1 divided by whatever is R1 plus JX1. That will be my I1. And this I1, what I get as the primary current under load condition, will bounce back to such a value that it will be exactly equal and opposite to that of the secondary ampere turns or secondary MMF I got because of the load being connected. The secondary ampere turn was I2 multiplied by N2. This is what is the secondary MMF. Right? Yeah. I1 is the current that has suddenly increased in the primary. I0 was the original current which established the flux when the transformer was not loaded. I1 is the new current that has suddenly come up in the primary because the flux was trying to collapse and E1 has gone to very low values. So suddenly a new current has jumped up in your primary winding. Right? Now, this I1 will reach to such a level exactly that it would be equal and opposite to that of N2 I2. So we come back to the original flux level itself as far as the core is concerned. So this essentially tells me that this I2 N2 should be equal to I1 N1, where this is the new current established in the primary winding. Obviously, I will still have this I0 present. I am not saying that has gone away, but this I0 is minuscule as compared to the new value of I1. So I can just say, as an engineering approximation, I can neglect I0. Just forget about I0, and I would say that I1 N1 should be equal to I2 N2. So I can say I1 by I2 equal to N2 by N1. This ampere turn balance or MMF balance of all the windings of the transformer is true in any case of a transformer. Whether we are looking at instrument transformer, distribution transformer, power transformer, impedance matching transformer, isolation transformer, auto transformer. In every case, this ampere turn balance is valid. Right? See, we have got basically I2, N2 as the secondary ampere turns which were trying to kill the primary or originally established flux. Now, the primary is bouncing back. It is not allowing the flux to be killed. So, it is essentially again trying to circulate a current which is corresponding to I1. It is bouncing back. And it will circulate such a current that it will nullify whatever is the new opposition it has faced from the secondary side. Only then it will return back to the original condition itself. So, I have to have I1 N1 as the MMF which will oppose I2 N2. Both have to be equal but opposite. Only then I will come back to the original status.